Welcome to the Clear to Operate V plus R test pyramid training video for the 22X demonstration. Let's go to the first part of the demo. As detailed out in the technical README document, the CTO user is shared by two demonstrations. So once you log into the dashboard, you have to navigate to the right demo dashboard called V plus R test pyramid. Once you're in there, you can move to the tab 0 where an outline of the demo will be displayed. These are the steps that you need to follow in order to complete the demo. Each step highlighted in the outline slide corresponds to a different tab in the demonstration dashboard. Let's move to the first one called Regulatory Requirements. Minimize the Relations panel as it will be useful later on. Now let the Part 25 from the FAA CFR load. Once it's loaded, you can browse the full set of regulatory requirements from it. We have used the Rectify solution to import the full Part 25 into the 3DEXPERIENCE platform and turn it into a structure of requirements. Each individual regulatory paragraph from this body of regulations has been turned into an identifiable requirement object in the platform with its own lifecycle control and configuration management. The red wire for the demonstration will be the 25.562 requirement, which has to do with emergency landing conditions, otherwise known as survivable crash events. Here, all of the conditions that an aircraft needs to comply with in order to show survivability are detailed out. As you can see, the Rectify solution has allowed us to import the requirements, including rich text and images. Moreover, each requirement we need to show compliance with is connected to a test case that defines the tests needed to show said compliance. Let us now move to the second part of the demo, where we'll define the V&V strategy to put in place. The goal of the demonstration is to show crashworthiness compliance with virtual means only. In order to do so, we have decomposed the top-level physics or phenomena of interest into its fundamental building blocks by the means of a V plus R, so virtual and real, test pyramid. At each level of the pyramid, we have defined a V&V test plan. The top level one is on product certification, and the lower tier ones are there just to build confidence on the fact that the simulation models to be used are predictive enough. This is part of a simulation credibility assurance framework. Let us now move to the top level test specification. As you can see, it contains a description that signifies or that explains what the tests are all about. The requirements that it is used to show compliance with are contained in Part 25. It has to do with the N101 program, and all of the tests will be scheduled in a specific project. Inside it, we have several things. As you can see, here we have the level 3 test specification. Beneath it is the level 2 one, so they are connected. This means that in order to execute level 3 tests, we must have executed level 0, level 1, and level 2 tests. We also have a test case. The test case will gather the test specifications in order to show compliance with one or several requirements, in our case 25.562. As you can see, it contains a test script that will aid test engineers in executing or preparing the different test procedures to be carried out. As we said before, each test specification and the test cases beneath it show or serve to show coverage of specific requirements, in our case, regulation requirements. As we said before, there is a notion of dependency or precedence, prerequisites, so to speak, between the different test specifications in our V plus R test pyramid. Level 0 must be executed prior to level 1, which must be executed prior to level 2, all the way to level 3. If we show the level 2 tests, we will see that this is the last stage in the pyramid where we perform correlation. So there is a virtual test and a physical test that are executed back to back in order to show the predictiveness or to correlate the simulation models. If we go down to level 1 and level 0, those are the test specifications where the most test cases are planned. This is pretty easy to comprehend or to understand because in the lower levels of the pyramid is where we gather the most information necessary to validate the predictiveness of our virtual models. So going down to the lowest level, we can see that inside each test case, there is one or several test executions. The test executions are the places where we will actually deliver the test results and the conclusions from the tests we have performed or we will perform. In level 0, we see that the different tests and the requirements that they cover can be shown in a matrix view to easily identified which requirements are covered and which are not. So if we go back to the test specifications and we dive a little bit deeper in the test scripts, we will understand what they are all about. Test scripts can be stored in company-wide libraries, and they serve to define standardized testing procedures to carry out specific types of tests. For example, the one that we're showing on the screen defines the standard procedure for uniaxial tensile tests of metallic components. Let us now move to the third part of the demo where we plan the tests that we have defined. As we saw earlier, the test specifications are connected to projects. So each test execution planned within a test specification is automatically placed inside the relevant project. Here we have scheduled them. We have defined the different due dates and the different assignees. And where it is relevant, we have defined precedence links between the different tasks. If you go into the collaborative tasks, you will be able to filter the content just to see the different test executions. So if we put the project context level 0 tests, we will see only the test executions that are planned beneath the test. And remember that each test execution is simply a specialized collaborative task. So it has assignees, an owner, and you can deliver you can put attachments on it and place deliverables inside the task. If I assigned a new person, so in this case myself, to another task and I move it to in work, I receive a notification telling me that I have to work on the specific test execution that we have just seen. So this is a nice way to manage the test execution and to track the execution throughout the company. We'll now focus on the first one. Let us now move to the first execution part of the demo. In the coupon level tests, so level 0 or the lower tier tests, we have both real and virtual plus real, so calibration tests. Inside the test execution for the real test, we have a results capture or capture results panel. Here we can check that we have completed all of the necessary steps in the test script in order to extract the necessary information from the test. Moreover, we have delivered inside the 3DEXPERIENCE platform a relevant document summarizing the findings of the test, which we can directly attach to the capture results panel inside the test execution. After having flagged the execution and the results as conclusive or passed, we can validate the test execution and flag it as passed as well. It'll now be in review. After it's been reviewed, we can simply complete it in order to perform the V plus R calibration test. Because there's a precedence link between these two test executions, if we do not complete the real one, we cannot start the V plus R test. As you can see, there's an item under test attached to the test execution, which is a standard ASTM E8 tensile test coupon. This is the one that we will use to perform the virtual and the calibration tests. So you can now simply play the video that is attached in the dashboard to see how this plays out on native apps side. We begin by exploring the tensile coupon test to see how it's built. As you can see, it is built according to the specifications defined in the relevant ASTM document. Inside it, we also have an abstraction shape and a final element model, so a container for the mesh, which is used to configure the, the first virtual test execution. The goal here is to very closely mimic the experimental setup that was used for the physical test in the virtual environment. And because we very closely mimic what has happened on the virtual test, on the physical test, sorry, we'll be able to use it as a template for calibration. The first test execution on the virtual side was carried out on a dummy material, which will be used for the calibration procedure. We import the force versus displacement data from the real test into the platform, and using the SIMULIA material calibration app, we select the simulation object that we defined just earlier to start the material calibration procedure. Once we have defined what the object or what the simulation object will be for the calibration, we can also define the parts of the material properties that we will calibrate. In our case, it'll be the elastic and plastic properties. So we start by giving some estimates of the uh, of the material properties, and then the system will perform an optimization procedure in order to make the virtual curve match as closely as possible the physical test curve. Once the results are close enough, so the objective function has reached a value that's close enough to 1, we can say that the material has been calibrated. Of course, inside the 3DEXPERIENCE platform, you can review the simulation results in the dashboard directly, and you can see different types of information, such as the mesh quality or the different field results, like displacement, plastic strain, von Misses, and so on and so forth. So now we move back to the V plus R test execution, and like before, we will deliver the test results. In this case, we have two simulation objects, one that was used as the entry for the calibration and the one used for the calibration per se. We deliver them, we flag the results as passed, and then we can flag the whole test execution as passed and submit it for review. After having completed the level 0 test, we move to the level 2 ones where we perform the last virtual and real correlations. As you can see, this is the place where we perform the cargo floor level correlations. So we have a large subassembly where we will perform back-to-back virtual and real tests to confirm or to adjust the virtual models and make sure that they are predictive. Inside the test specification, you can see that we have the virtual, the real, and the calibration test cases. Because we did not actually perform a real test, we will focus here on the virtual test execution. Like before, you can just put the video on full screen and let it play. Here, we will quickly show how the lower cargo floor level mesh was built using the structural model creation application inside the 3DEXPERIENCE platform and the model assembly capabilities. So we start by defining the contributing final element models after having defined the contributing shapes that will serve to the assembly of meshes FEMREP in order to make sure that we are considering only the necessary meshes. After that, we can check the different ties that glue the meshes together and move to the scenario definition. This scenario was inspired by the actual physical and virtual tests carried out by Airbus when going for the virtual crashworthiness certification of the Airbus A350. So we have a falling mass test. The virtual model is placed on a static rig, and a falling mass is impacting this assembly. We extract the necessary information, and in this case, we hint that the correlation between the virtual test and the physical test is good enough to check to certify that our models are predictive. Like before, we can review the virtual test in the 3D dashboard and just show that the rich results from the 3D Experience platform's native apps can be very easily visualized and shared throughout the whole company using a dashboard. Like before, we now move to the Capture Results tab, where we check that the different test steps were carried out without an issue, and we deliver the simulation object that we just saw. So like before, we select the right physics simulation object, we deliver it, we flag the capture results as passed, and then we flag the test execution itself as passed before putting it in review. We can now finally move to the top level tests on the full fuselage section or barrel. Here we will see how the simulation environment was created from the master engineering bill of materials, or the master DMU, how it was meshed semi-automatically, and how we configured the execution for the virtual tests. As you can see, there is a link between the master engineering DMU and the two versions of the simulation environment that were used for different tests. Like before, just let the video play and you'll see how this plays out. On native app side, we open the simulation environment for the fuselage section, and inside the collaborative lifecycle for native apps application, you can bring out the different revisions. In the metroline revision panel, you can navigate towards the original engineering DMU that was used to create the simulation environment. You will see that by comparing the two structures, the simulation environment is just an advanced application of the master engineering data, so it can be seen as a PLM branch of it. The newly acquired SIMULIA capabilities of compare and merge allow us to synchronize both structures in case of a change on the master engineering data. So after having compared the structures to see how they differ, so which parts of geometry have been added or removed, we move to the material definition inspection. We see that we are using inside the simulation environment the different materials that we calibrated in the previous steps or the previous tiers of the pyramid. We now move to the model definition. Much like before, we will go for a rule-based meshing procedure, which can be seen as a semi-automated meshing procedure. After having defined the part that we want to mesh, and after having defined the meshing rule, we can just run the automated meshing scripts from the platform and create, uh, well, as easily as possible, some meshes for the relevant parts. Of course, this procedure works well on simple parts. On the more complicated parts, typically what will fail is the mid-surface extraction, so it will require some manual intervention. But for simple parts, the automated mid-surfacing and meshing works pretty well. We can now move to the definition of the virtual test, which is a vertical drop test. So, inspired from the regulation, we define the vertical speed that the fuselage will need to impact the floor with, and we let it get crushed under its own weight. because we have a very dynamic event where we will experience massive deformation and failure of parts. Having a proper contact definition is important. As we said before, the only load placed on the model is gravity, which will make it impact the floor and crash under its own weight. Just for reference, this simulation takes about 2 hours to run on 52 cores. So consider that if you want to open the simulation model and run it yourself on your end. We monitor the execution throughout, and after the simulation reaches its completion, we review the results, which show massive failure, so a non-satisfying behavior. It is now time to deliver the first test results. We now move to the next tab of the demonstration dashboard, top level barrel virtual test. As you can see, we have a test execution which contains a specific test script. This test script is the one that we followed to perform the first virtual test. It contains a simulation process template used to correctly define the virtual test. In the Relations panel, we can see that there's a full traceability between the CAD model, the mesh, and the simulation object used for the first test that we carried out. As we saw earlier, the first test that we carried out showed a massive failure of the lower part of the fuselage, meaning that the deceleration profile was too high. This means that the first design of the fuselage section is not compliant with the crashworthiness regulation. The results are then flagged as failed, and it is the same case for the test execution as a whole. After flagging it as failed, we submit it for review. Do not forget that like we did for the other simulations, we can review the test execution results in the web environment. Because of the unsatisfying results on the first version of the fuselage that was submitted for the virtual test on crashworthiness, a design improvement loop is launched. In the issue panels that we see, we have a 3D window that highlights the different issues that have been raised on the fuselage section. On the left panel, we have an application called issue management, which allows us to review the different issues that are clicked on the right panel. As you can see, there are several issues declared on different parts of the fuselage that were raised by the CTO user assigned to other people, and that were discovered thanks to the simulation that we performed just earlier. The simulation and a 3D markup object are attached to the issue to further document it. The simulation serves as a proof that the issue is valid, and the 3D markup that's attached to it serves as a means of documenting the issue a little bit further. This way, the people assigned to the issue and the designers tasked with resolving them will have a clearer view on what's expected of them in order to resolve the issue. On the two other issues declared on other parts of the fuselage, we also see the simulation and the 3D markup as attachments. Let us open the 3D markup to see what the issue is all about and how it was documented. 3D markups can be viewed as 3D PowerPoint presentations. They take the model-based 3D definition of the product and enrich it with annotations, measures, or sketches. This is what we see on the screen right now. As you can see, different parts of the 3D markup tie to different parts of or different issues that were raised on the fuselage, which were discovered thanks to the simulation that we executed and the failed test that corresponds to it. In order to treat the issues, a formal change process can be initiated. We can now finally jump to the last part of the demonstration. We move again to the level 3 test specification, which gathers the different test executions virtual test executions needed to show compliance with crashworthiness regulation. Like before, we review the content of the test specifications and move to the test case that ties to or that shows coverage with the emergency landing conditions requirements. Like we saw before, the first test execution, which has failed, relies on the first version of the fuselage. The second one relies on the new improved version of the fuselage that takes into account the findings of the first test. The same test that we executed for the first version is ran on the second one, and the results are compared back to back. As we can see, a reinforcement on the cargo floor has been added, and this yields much more satisfying results on the same test case. The fuselage still crashes, but the failure is managed on a much better way. So we move to the second test execution where we have yet to deliver the results, and we do precisely that. We check that the test was carried out like it was supposed to, and we search for the simulation object that we just reviewed on the web environment. We delivered it as proof that the test was passed, and we flag the results as passed. We now finally move to the test execution, and we flag it as passed before submitting it for review.